Hi, thank you for joining my virtual session. I'm Sébastien Le Fouest from Karen Mulleners' lab here at EPFL. Today I'll talk about vertical axis wind turbines undergoing dynamic stall. More specifically, I want to look at the asymmetry in the flow physics between two halves of a blade rotation. But why do we look at vertical axis wind turbines in the first place?
Vertical axis wind turbines are great candidates to complement traditional wind turbines in our goal to increase the share of energy consumption captured from the wind. Many features make these turbines attractive for decentralized power production, including quietness. Vertical axis turbines produce 3 times less noise than traditional turbines, insensitivity to wind direction, ease of maintenance and commissioning, and also they are frankly rather beautiful. These features make vertical axis wind turbines ideal for urban applications.
The limiting factor to the development of vertical axis wind turbines is the occurrence of dynamic stall on the turbine blades. Before we get into the details, let's look at the aerodynamics of a vertical axis wind turbine blade.
The effective flow conditions on a turbine blade result from the vectorial combination between the incoming flow velocity and the blade velocity. This results in a periodic variation of the effective angle of attack and velocity acting on the blade occurring over each blade rotation. The magnitude of the effective flow oscillations is governed by the ratio between the blade velocity and the free stream velocity, also known as the tip speed ratio. The smaller the tip speed ratio, the greater the oscillations. For low tip speed ratios, typically below 3, the effective angle of attack exceeds the blade's static stall angle, leading to the occurrence of flow separation and dynamic stall. Dynamic stall involves the formation of large-scale coherent vortices followed by massive flow separation. Flow separation is associated with a loss of turbine efficiency. Vortex shedding causes heavy load transients that vary cycle to cycle, potentially causing structural failure of the turbine blade. To tackle this issue, we decided to experimentally investigate the timescales, unsteady loads, and flow structures on a wind turbine blade undergoing dynamic stall. So let's check out our experimental apparatus. We placed a scaled-down model of a vertical axis wind turbine in our recirculating water channel at EPFL. We captured time-resolved PIV at 1000 Hz using a high-speed laser and camera. The laser produces a light beam which passes by a beam splitter to generate 2 light sheets that cut the turbine blade at midspan. The turbine was operated at a tip speed ratio of 1.5 for 19 full rotations. We keep the blade in the field of view at all times thanks to a rotating mirror system, which we'll look at in more detail in a moment.
But first, let's have a look at our wind turbine model. Our scaled-down Darius wind turbine model is motor-driven. It has 2 interesting features. Firstly, this stepper motor here allows us to continuously adjust the blade's angle of attack independently of the main rotation. Note that for this experiment, we kept a fixed pitch. Secondly, a built-in load cell allows us to retrieve the unsteady aerodynamic loads acting on the blade. This load cell was built using 10 strain gauges, which allow us to form 5 full Wheatstone bridges. The signal is amplified here directly on board before it's transmitted to the slip ring in the center. This load cell allows us to retrieve the shear forces acting in the radial and tangential direction to the blade's circular path, as well as the pitching moment acting at the quarter chord of the blade. To obtain flow measurements with satisfactory spatial and temporal resolution, we assembled a spinning mirror apparatus.
2 45-degree mirrors are rotating about an axis which was aligned with the turbine's axis of rotation. The outer mirror is placed at the same radius as the turbine blade and reflects its image onto the central mirror. The central mirror reflects the image downwards through a hollow shaft onto a third stationary 45-degree mirror. The camera looks into the stationary mirror, capturing a close-up image of the developing flow every millisecond.
Now we've covered the experimental setup, let's have a look at some of our results.
We will start by looking at an overview of the temporal evolution of the flow field and unsteady loads developing over one turbine rotation. On the left, we'll see the temporal evolution of the normalized vorticity around the wind turbine blade, while on the right, we'll see the corresponding total force coefficient experienced by our blade. The shaded regions correspond to the periods of time when the blade's angle of attack has exceeded its static stall angle. The shear layer appears to be fully attached as the blade begins the upwind half of its rotation. Once the effective angle of attack exceeds the blade's stall angle, we note the appearance of flow reversal occurring on the blade, resulting in a rapid increase in total force. Following that, we observe the formation and growth of a large-scale dynamic stall vortex, which will eventually result in a force maximum. Once the vortex reaches a chord-length diameter in size, it pinches off and it entrains counter-rotating vorticity in the blade's vicinity. Vortex pinch-off leads to a rapid drop in total force. Halfway through the revolution, the vorticity accumulated in the dynamic stall vortex is still dissipating. The flow is massively separated and we reach a force minimum. As we enter the second half of the rotation, the flow remains separated. We do note a second accumulation of vorticity in the second half, resulting in a local force maximum. However, it lacks coherence to be considered a second dynamic stall vortex. As the revolution ends, the flow reattaches and the blade enters upwind conditions once again.
To assess the timescales related to flow separation, we had a closer look at the quarter chord pitching moment coefficient. According to thin airfoil theory, a symmetric airfoil, the quarter chord should coincide with the blade's aerodynamic center. This means that any deviation of our pitching moment coefficient measured at the quarter chord from 0 is related to flow separation.
Here we look at the temporal evolution of the pitching moment coefficient superimposed for all 19 rotations. All curves peak at a clear minimum around 0.3 periods, which coincides with the occurrence of vortex pinch-off. We compute the time span between the moment when the blade exceeds its static stall angle and pinch-off, also known as the dynamic stall delay, here shown with a gray arrow. In the upwind half, the dynamic stall delay was found to be 3.4 convective times on average, based on the blade's chord and velocity. This falls right into the optimal vortex formation time, found to be between 3 and 5 convective times for symmetric airfoils. In the downwind half, the blade only has 1.3 convective times to form a dynamic stall vortex, which is insufficient. The pitching moment does not return to a constant value near 0 until about 0.9 periods. This suggests the flow remains fully separated from the blade from 0.3 to 0.9 periods.
The initial state of the shear layer is another important difference between the upwind and downwind halves. To get a better understanding of the shear layer state, we took a look at the temporal evolution of the circulation around the blade.
There is no circulation at the beginning of the upwind half. Circulation sharply decreases up to the point of pinch-off determined earlier around 0.3 periods. A plateau is reached and maintained until the beginning of the downwind half. Our flow measurement snapshots also highlight the important difference in the state of the shear layer between the two instances when the blade exceeds its static stall angle. For the upwind half, here snapshots B and C, the shear layer is initially attached and the normalized circulation is above -1. However, for the downwind half, here snapshots D and E, the shear layer is fully separated and the normalized circulation is at its minimum value of -3.5.
At this point, we wanted to quantify the influence of the surrounding vorticity on the effective flow conditions acting on the blade. To do that, we computed the vortex-induced velocity at the leading edge by completing Biot-Savart's integral over our entire field of view.
Here, we look at the ratio between the induced velocity at the leading edge and the blade velocity, which is the characteristic velocity of our system. The induced velocity is below 20% of the blade velocity before the blade exceeds its static stall angle. The formation of a large-scale dynamic stall vortex leads to a dramatic increase in the induced velocity, reaching 90% of the blade's velocity around 0.3 periods. The snapshot in C shows how the flow is dominated by the coherent large-scale structure forming on the blade's leading edge. The induced velocity remains significant up until 0.9 periods.
To quickly summarize, vertical axis wind turbines make great candidates to diversify wind turbine technology, but they suffer from dynamic stall. We carried out an experimental investigation of a vertical axis wind turbine model undergoing dynamic stall, acquiring time-resolved, PIV, and unsteady load data. We observed a significant asymmetry in the flow physics between the upwind and downwind half of the blade rotation and identified three main reasons for it.
Vortex formation time. The blade kinematics allows sufficient time for optimal vortex formation in the upwind half, but not in the downwind half. Secondly, the shear layer is initially attached for the upwind half while fully separated at the beginning of the downwind half. Lastly, the vortex-induced velocity at the leading edge is much more prominent in the downwind half compared to the upwind half.
Thank you for listening to my video, and please feel free to ask me any question.